What really are the stars that light up our sky? Dear traveler, good day. Today, we look up to these points of light that seem fragile, but are actually titans of fire, cosmic forges where the very matter of life is born and dies. Each star is a beating heart, fusing hydrogen into light, shaping the universe for billions of years. Some fade softly, others explode in cataclysms so violent that they shake space-time. And if each star in our sky hid, deep down, the secret story of the entire universe. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. We penetrate the vastness of the starry sky to explore our cosmic neighborhood, where our star, the sun, reigns, and where a few luminous points, though distant, are our closest stellar companions. Imagine yourself floating in space, observing the sun's golden glow and feeling the warmth it diffuses. For millennia, civilizations have gazed at it as an inexhaustible source of energy and fascination. In this first stage, we will draw its physical portrait, then we will move towards Proxima Centauri and Alpha Centauri A and B, three neighboring stars that pique our curiosity. We will then discover how their stellar wind could influence potential habitable planets and what surprising information the neutrinos and radio waves they emit bring us. Let's start with the sun, this gigantic sphere that lights up our days. Its diameter reaches about 1,400,000 kilometers, more than 100 times that of the Earth. Its mass is such that all the planets of the solar system seem insignificant in comparison. It is composed mainly of hydrogen and helium, with small proportions of heavier elements such as oxygen, carbon, and iron. These elements are in a plasma state, where electrons are separated from atomic nuclei by the extreme heat. At the surface, called the photosphere, the temperature is around 800 degrees Celsius. At the core, in the nucleus, it reaches about 15 million degrees, enabling the fusion of hydrogen into helium and releasing colossal energy. This nuclear fusion is the source of the sun's light. The produced photons take thousands or even hundreds of thousands of years to reach the surface before traveling 150 million kilometers in 8 minutes to the Earth. When we look at it, we see it as it was a few moments earlier. The sun also emits a constant flux of ionized particles called the solar wind, composed of protons and electrons projected at high speed under the influence of its magnetic field. This flux forms a spiral that extends far into space. Near Earth, it can disrupt electrical systems, damage satellites, and cause magnificent auroras. Planets react differently to this wind, depending on their atmosphere and magnetic field. Venus, devoid of magnetic protection, is more exposed, while Earth is partly shielded by its magnetosphere. The sun serves as a reference for astronomers. Upon discovering a star, they compare it to him, evaluating its luminosity, size, and temperature. Classified among G-type stars, it provides a model for understanding the structure and life cycle of other celestial bodies. Moving away from Earth, we cross the void separating the sun from its closest neighbors. After a journey of several light years, we reach Proxima Centauri, located a little over 4 light years away. Despite this relative proximity, our current vessels would take tens of thousands of years to reach it. Proxima Centauri is a red dwarf, smaller and cooler than the Sun, with a surface temperature of around 3,000 degrees. Very common in the galaxy, These stars are crucial for the search for habitable planets. But their intense magnetic activity can release flares, capable of sweeping away the atmosphere of nearby planets. In 2016, an exoplanet, Proxima Centauri b, was discovered in its habitable zone. It could have liquid water if the atmospheric conditions allow it, but its proximity to the star likely subjects it to a bombardment of particles, complicating the survival of a stable atmosphere. Continuing our journey, we encounter the Alpha Centauri system, composed of Alpha Centauri A and B, accompanied more distantly by Proxima. Alpha Centauri A is very similar to the Sun, with a surface temperature close to 5,700 degrees, while Alpha Centauri B is slightly cooler, around 5,200 degrees. These differences influence their luminosity and activity. Their stable and close binary system has been studied for a long time, especially in the search for planets. The magnetic activity of these stars is a key factor for potential habitability. Frequent flares or powerful stellar winds can erode atmospheres. In a multiple system, the interaction of winds can also alter habitable zones. The radiation and particles emitted by the Sun and its neighbors produce fascinating phenomena. Neutrinos, almost elusive particles, pass through matter without interacting. Billions pass through our bodies every second. Their detection confirms nuclear fusion models. Those emitted by other stars are harder to capture, but could reveal their internal structure. Radio waves, on the other hand, originate from magnetic storms and other energetic phenomena. On the Sun, they are linked to sunspots, the corona, and flares, varying according to an 11-year cycle. They help us better understand the dynamics of its outer atmosphere. In Proxima Centauri, they reveal the intensity and frequency of its flares, crucial for assessing the habitability of its planets. For Alpha Centauri A and B, they provide insight into differences in their magnetic activity and complete optical and infrared observations. All these clues, from neutrinos to radio waves, form a puzzle where habitability depends not only on the distance to the star, but also on the robustness of the atmosphere and magnetic protection. Earth benefits from a robust magnetic field, unlike Mars, which has lost most of its atmosphere. For Proxima Centauri b, uncertainty remains. It could be protected or, on the contrary, exposed. Spectroscopy could one day reveal the presence of water or atmospheric gases. Alpha Centauri might also harbor planets, but their detection is complex. Modern techniques of measuring stellar oscillations or high-contrast imaging bring this dream closer to reality. Our immediate stellar neighborhood, composed of the Sun, Proxima, and the Alpha Centauri duo, already illustrates the diversity of stars. By studying them, we understand that the cosmos is not uniform. Each system has its own conditions and challenges for life. The Sun remains our benchmark. Proxima represents the longevity and unpredictability of red dwarfs, and Alpha Centauri embodies the complexity of binary systems. Technological advances, from space telescopes to giant radio telescopes, sharpen our observations. We link radio signals to magnetic phenomena and stellar winds, comparing their intensity and frequency to those of the Sun. Thus, without leaving our neighborhood, we observe a wide variety of stellar behaviors and their effects on planets. This natural laboratory allows us to understand the internal processes of stars and their interaction with their environment. Each technological progress brings us closer to the detection of potentially habitable worlds, refining our understanding of the link between stellar activity and planetary viability. In a few decades, our perception of the sun and nearby stars has radically changed. From distant luminous objects, they have become living and dynamic systems. Their neutrinos and radio waves tell us their story and invite us to continue the exploration. This first step of our journey already shows the richness of contemporary astrophysics. The sun serves as a standard. Proxima reveals the frequency and challenges of red dwarfs. Alpha Centauri opens us to the complex dynamics of binary systems. In each of these cases, the search for life remains the guiding thread that directs our instruments and questions. At the end of this exploration, let us remember that our stellar neighborhood is anything but mundane. It is the permanent theater of colossal energies that shape worlds and perhaps give molecules the opportunity to create life. This is only the beginning of a long journey, where each advance offers us a new perspective on the cosmos. In the vastness of the Milky Way, myriad stars are revealed, among which red dwarfs hold a special place. Their soft, reddish glow indicates a surface temperature lower than that of massive stars. Although they are not very bright, they represent the majority of the stellar bodies in our galactic environment and are distinguished by unique physical properties. To understand their essential role in the cosmos, we will explore their mass, energy, lifespan, and magnetic activity, as well as the impact of their atmospheres on the surrounding planets. Finally, we will discover some emblematic star systems, such as TRAPPIST-1, Barnard Star, and Luyten b, which illustrate the fascinating diversity of these stars. Red dwarfs make up about 3/4 of the stars in the galaxy. This abundance results from the conditions of stellar formation in clouds of interstellar gas and dust. When these clouds collapse under gravity, the final mass of the star depends on complex processes. Often, the result is a low-mass star, less than half the mass of the Sun, classified as a red dwarf. With partial or modest collapses being frequent, these small stars end up dominating the stellar population. Despite their large numbers, they emit little energy. Their brightness is limited by their size and temperature, which ranges from about 2,400 to 3,500 degrees Celsius, compared to about 5,500 for the Sun. This difference explains their red color and their faint visibility to the naked eye, even when nearby. Only instruments can identify these discrete neighbors. Like all stars on the main sequence, they produce their energy by fusing hydrogen into helium. Their low mass does not allow them to reach the extreme temperatures of larger stars, slowing the fusion rate. This makes them less bright, but grants them an exceptional longevity of several 100 billion years, well beyond the current age of the universe. Many have been shining since the early days of the galaxy, and will continue to do so long after stars similar to the Sun have disappeared. They are not calm, however. Their surface can be covered with vast dark spots due to their magnetic field, and they sometimes experience violent eruptions ejecting particles and radiation. These flares, sometimes super flares, can alter the atmosphere of nearby planets and affect their habitability. Around them, the habitable zone is found very close. The planets that orbit there are often in synchronous rotation, always exposing the same face to the star, which creates strong thermal contrasts. The eruptions in proximity make it difficult to maintain a stable atmosphere. Yet, the colossal number of red dwarfs means even a small proportion with habitable planets represents a vast potential.
you still dance with me when the party is...
Among notable systems, TRAPPIST-1 is located 40 light-years away. This very cool star, about 2,500 degrees Celsius, hosts 7 planets comparable in size to Earth, several of which are in the habitable zone. Their orbits are extremely short and mutually influenced, offering a dynamic spectacle. Its low brightness facilitates the detection of transits, allowing for the analysis of atmospheres and compositions in search of life-related gases. Another notable neighbor, Barnard's star, 6 light-years away, has a high proper motion and a mass equivalent to 1/6 of the Sun's. In 2018, a super-Earth was detected there, probably icy, but still of scientific interest. Its proximity allows for detailed monitoring with powerful instruments. A third example revealing the diversity offered by red dwarfs concerns the red dwarf GJ273, often called Luyten's star, 12 light-years away, hosting Luyten b, a super-Earth located in a potential habitable zone. Discovered by the radial velocity method, it could have a temperature compatible with the presence of liquid water if it has a suitable atmosphere. This system also attracts attention for possible attempts at interstellar communication. Astrophysically, red dwarfs are distinguished by total internal convection, preventing the formation of an inert helium core and prolonging their stable phase. Their magnetic activity offers valuable study opportunities to understand stellar magnetic fields. The protoplanetary disks surrounding them, though less luminous, can give rise to solid or massive planets. Their proximity to the habitable zone often implies synchronous tides, intense thermal exchanges, and frequent impacts from stellar particles. The exploration of exoplanets around red dwarfs fuels the hope of discovering life. If life emerges in such an environment, it would have billions of years to evolve. The next telescopes will seek to detect telltale molecules in their atmospheres, which would upend our view of the universe. TRAPPIST-1, Barnard's star, and Luyten b illustrate the variety of worlds orbiting red dwarfs. Surveys of transits or radial velocities excite curiosity, sterile planet or habitable world. Their low luminosity makes spectral study easier, feeding the hope of one day detecting gases associated with life. The immense stability of these stars allows monitoring of their magnetic activity and its effects on planetary atmospheres. Their slow but continuous contribution to enriching the interstellar medium also shapes galactic evolution. Some approach brown dwarfs, too low mass for stable fusion, but too massive to be giant planets. Despite this diversity, they dominate in number, invisible to the naked eye, yet omnipresent in the galaxy. In a distant future, when massive stars have disappeared, they will continue to quietly illuminate the galactic outskirts. They might be the last possible refuge for life. Through their constancy, they remind us that greatness can lie in discretion. Red dwarfs are everywhere yet rarely seen. They testify to the extraordinary diversity of the cosmos, where the minuscule and the immense combine to compose the symphony of stars. Brown dwarfs, sometimes nicknamed aborted stars, intrigue with their ambiguous position between star and giant planet. Little known to the general public, they are overshadowed by the shine of stars or the attraction of planets in our solar system. Yet, they offer valuable insights into the formation and diversity of celestial bodies. we will delve into their universe, exploring their birth, characteristics, classification, and understanding why they cannot shine like true suns. We will also see their role in the dynamics of stellar clusters and what they reveal about certain aspects of dark matter. Finally, we will discover the fragile balances of binary systems associating red dwarfs and brown dwarfs, which offer researchers a unique field to test the laws of gravitation and redefine the boundary between star and planet. The transition between giant planet and brown dwarf rests on a threshold, about 13 Jovian masses. A Jovian mass corresponds to that of Jupiter. Beyond this threshold, an object can trigger the fusion of deuterium, a rare isotope of hydrogen, at lower temperatures and pressures than ordinary hydrogen fusion. Brown dwarfs thus succeed in their youth in producing energy by burning this deuterium. But this partial fusion is brief and insufficient to sustain stable radiation. However, above roughly 75 Jovian masses, hydrogen fusion begins, and the object becomes a true star. Between these two thresholds lies the entire range of brown dwarfs, forever blurring celestial classification. To visualize this threshold, imagine a cloud of gas and dust collapsing. In a star in gestation, the temperature increases until it triggers hydrogen fusion. But if the pressure remains insufficient, only deuterium can fuse. It's an ephemeral fireworks display, unable to maintain a brightness comparable to an ordinary star. Brown dwarfs stop at this stage. They shine faintly at first, then slowly fade, like embers that never caught fire. From afar, this initial glow can deceive and cause hesitation between a small star and an overgrown planet. But when deuterium fusion ends, their weak luminosity reveals their nature, a fragile heat source cooling over billions of years. Astronomers classify brown dwarfs using a spectral scale, L, T, and Y. L-type brown dwarfs are the hottest, around 2,000 degrees Celsius. Their color is orange-red, and their spectra show water vapor, carbon monoxide, and sometimes metals like iron or titanium. Their atmosphere retains certain compounds in a gaseous state before they cool down to form silicate clouds. T-types, cooler at below 1,200 degrees, display strong methane signatures. Their radiation is mostly infrared, which explains why their discovery awaited the rise of specialized telescopes. Their atmosphere contains silicate or metal clouds, sometimes crossed by storms similar to Jupiter's. Y-types, finally, are the coldest, sometimes below 300 degrees. Their spectrum reveals ammonia, marked methane, and other rare molecules. For a long time, they were debated whether to be classified as giant planets, but their formation and initial deuterium fusion still set them apart. The abundance of brown dwarfs in the galaxy remains a subject of study. They are less numerous than stars, but much more common than random chance would suggest. In open clusters, they are often found in a notable proportion. The more massive ones sometimes expel the lighter ones, creating rogue brown dwarfs wandering in interstellar space. Understanding their number and distribution refines our models of stellar formation and cluster dynamics. Some have considered that they might constitute a significant part of cold, dark matter, this invisible mass that does not emit light. But recent surveys show that they represent only a small fraction of it. However, these studies have helped to better inventory brown dwarfs and clarify their distribution. Binary systems of red-brown dwarfs are particularly interesting. Red dwarfs are already low-mass, low-luminosity stars. In close pairs, their balance is unstable. Tidal forces and energy transfers can disrupt their evolution or even cause material exchanges. The eruptions from the red dwarf sometimes bombard the brown dwarf, altering its atmosphere and chemistry. Observing these systems requires highly sensitive infrared telescopes and the analysis of radial velocity variations of the red dwarf. Technological advances today allow for a better understanding of these pairs and reveal how much the star-planet boundary becomes blurred when they interact. The study of the atmospheric composition of brown dwarfs reveals silicate dust, metallic oxides, or gaseous iron. As they cool down, these elements condense into clouds. The spectra change, marked by the appearance or disappearance of certain molecules. As they age, they slip from one spectral type to another, depending on their temperature and initial composition. In open clusters, brown dwarfs gravitationally interact with other members. Some end up being ejected into space, while others influence the orbit of their neighbors. These movements contribute to their dispersion in the galaxy and are part of the global balance of visible matter. Most are born by the gravitational collapse of a small gaseous core, like stars, but without reaching the necessary mass to fuse hydrogen. Others could form in protoplanetary disks and then be ejected. Ejection scenarios are common in dense formation regions, where gravitational encounters are numerous. Some brown dwarfs are reminiscent by their atmosphere of giant exoplanets. Studying them allows testing detection methods for water, methane, or other markers, and comparing their physics to that of exoplanets. Their rapid rotation and magnetic activity are also intriguing. Some emit radio pulses, evidence of robust magnetic fields, possibly linked to their internal structure or the influence of a companion. Modern instruments already make it possible to map the sky, searching for these faint glows and analyze their atmosphere. Future missions promise to reveal even colder brown dwarfs and explore their magnetic activity. Binary systems offer a natural laboratory to study mass transfers and orbital instabilities, enhancing our understanding of celestial mechanics. Neither fully fledged stars nor mere giant planets, they illustrate the continuity of nature rather than rigid categories. Their study sheds light on the mechanisms of formation and evolution of celestial bodies, challenges established boundaries, and reveals entire areas of the cosmos that have remained in the shadows. Witnesses of incredible complexity, each type L, T, or Y, reminds us of how many mysteries the universe still holds. The story of brown dwarfs is just beginning, and their exploration promises to continually renew our vision of the sky. Among the vast variety of stars that populate our sky, one category particularly attracts attention: the main sequence stars of type F, G, and K, which include our Sun. They are nicknamed the domestic fires of the galaxy because they offer stable and long-lasting energy on a cosmic scale. Designated by letters corresponding to their temperature and general properties, they can shine for billions of years, creating favorable conditions for the formation and evolution of planets and opening a window on the question of life in the universe. To understand these stars, one must delve into their internal structure. Imagine a giant onion formed of layers that collaborate to produce light and heat. At the core, hydrogen transforms into helium through nuclear fusion, releasing energy that radiates outward. This energy first passes through a radiative zone, where photons move slowly through dense matter before reaching the convective zone, where movements of hot and cold gas transport the energy akin to boiling water. Between the radiative zone and the convective zone, the tachocline marks a boundary where rotation changes abruptly. This contrast fuels the creation of powerful magnetic fields. In a G-type star like the Sun, magnetic activity cycles are observed, the most famous lasting 11 years and influencing the appearance of sunspots. This cycle also regulates the intensity of the stellar wind and the temperature of the chromosphere. The F, G, and K stars are differentiated by their temperatures and emissions. The F stars, hotter, reach between 6,500 and 7,500 degrees Celsius. The G stars, like the Sun, fall between 5,000 and 6,500, while the K stars are cooler, between 3,900 and 5,200. The hotter a star is, the more its light leans towards white-blue. The cooler it is, the more its hue becomes yellow or orange. In terms of longevity, the F stars live less long than the G and K stars because their higher mass accelerates their hydrogen consumption. However, they shine for 1 to several billion years. The G stars can last about 10 billion years, while the K stars, being more economical, can survive for several tens of billions of years. This duration plays a crucial role in the emergence of life. The habitable zone, where liquid water can exist, is farther from an F star than from a K star due to their difference in luminosity. But the long-term stability of this zone is critical. A too energetic star risks destroying the atmosphere of its planets, while a too weak star forces them to approach, which can harm the stability of their orbit. Metallicity, meaning the proportion of elements heavier than helium, strongly influences planetary formation. The higher it is, the richer the star's disk is in minerals and heavy metals, favoring the creation of rocky worlds or gas giants. Observations show that metal-rich F, G, and K stars often host more planets, but the presence of rocky planets also depends on the initial dynamics of the disk and gravitational interactions. Missions like Kepler or TS today allow us to refine our understanding of these links between stellar chemistry and habitability. Among the remarkable examples, the 61 Cygni system, 11 light-years away, brings together two orange K stars, smaller and cooler than the Sun. Its habitable zone is closer, and even if no Earth-like planet has yet been detected there, it remains a valuable laboratory for studying the behavior of binary K stars. 61. Cygni is also famous for being one of the first stars whose distance was measured by parallax, revealing the vastness of interstellar spaces. Tau Ceti, 12 light-years away, is a G-type star smaller and less luminous than the Sun. It has several planets, some of which might be in the habitable zone. Its lower metallicity makes it a case study on the impact of a lack of heavy elements. It is surrounded by a debris disk, comparable to an asteroid belt, which could either enrich its planets with water and molecules or threaten their stability through frequent impacts. Kepler 452, located 1/400 light-years away, is a G-type star slightly older than the Sun. Its planet Kepler 452b, a super-Earth, is in the habitable zone. Its discovery raises questions about the ability of older G-type stars to maintain conditions favorable to life despite their progressively increasing luminosity. The study of F, G, and K stars highlights a subtle balance between luminosity, metallicity, magnetic activity, and lifespan. These cosmic domestic fires can offer stable environments over billions of years, fueling the hope of discovering life elsewhere. Understanding their cycles, structures, and chemistry is key to advancing in this quest. Imagine in the depth of the night, an immense blaze simmering in the sky. This is a star that has reached an advanced stage of its existence, whose glow sets the space ablaze like a cosmic twilight. They are called red giants. Their blazing brightness, colossal size, and cooler surface than younger stars make them celestial marvels. A naive gaze would see only a red light, ignorant of the internal upheavals that stir them. Yet, their history and their role in creating essential elements reveal a constant alchemy in the universe. To understand them, imagine a journey through their atmosphere, outer layers, and down to their core, where nuclear fusion, gravity, and heat hold in balance. Red giants are born from stars with a mass similar to that of the Sun, sometimes a little larger. As long as they have enough hydrogen to fuse into helium, they remain stable, balanced between radiation pressure and gravity. But when this central fuel is depleted, fusion shifts to a shell surrounding a helium core. This transition triggers profound changes. The core, composed of helium, contracts under gravity, increasing internal temperature and pressure. In the upper layers, the fusion of hydrogen in the shell releases enough energy to expand the stellar envelope, increasing the overall size and cooling the surface. The star then takes on its red hue and bright luminosity. The red giant is born. At this stage, the central helium is inert and is in a so-called degenerate state, where the electrons create pressure that prevents complete collapse. Fusion continues around the core, while the core remains under tension, ready to ignite if a critical temperature is reached. When this threshold is crossed, helium transforms into carbon and oxygen by the triple alpha reaction. In medium-mass stars, this can occur explosively. It's the helium flash. After this release of energy, the core stabilizes and continues more calmly the fusion of helium. The star then becomes a major producer of carbon and oxygen, two pillars of chemistry and life. Convection then stirs the outer layers, bringing heat and fusion products to the surface. The envelope becomes a turbulent ocean that transports new elements outward. On the surface, the temperature drops to 3,000 or 4,000 degrees, much less than that of the Sun, giving the star its red color. Yet, its luminosity remains intense due to its immense surface, dominated by infrared radiation. Its weak surface gravity and expanded envelope create powerful stellar winds, ejecting gas, dust, and heavy elements into space. Over time, this material sometimes forms a planetary nebula, a bubble of ionized gas surrounding the glowing core of the star. Some red giants exhibit semi-regular pulsations, with their outer layers expanding and contracting, altering luminosity, size, and mass loss. These pulsations can even create true shockwaves in the envelope. Aldebaran in Taurus shines with an intense orange 67 light-years away. Larger and more luminous than the Sun, it could engulf Mercury, Venus, and part of Earth's orbit. Mira in Cetus changes in brightness every 330 days, sometimes becoming visible to the naked eye. It expels so much material that a long trail of gas and dust stretches behind it. Arcturus, in Bootes, one of the brightest stars, twinkles 37 light-years away, moving rapidly through the galaxy. These stars are not only spectacular, they shape the matter of the cosmos. The carbon and oxygen they produce spread into space, enriching clouds and future stars. Their light tells a cycle of creation and transformation that surpasses our perception of time. The Sun, in 5 billion years, will follow this path, swelling to possibly engulf Earth before becoming a white dwarf. Stellar winds, shells of gas, pulsations, and deep convection pace the slow agony of red giants. Astronomers study them using spectroscopy, photometry, interferometry, astrometry, and numerical modeling. Each observation refines our understanding of their structure and evolution. Some red giants expel their mass steadily, others chaotically, influenced by their initial mass, composition, and sometimes the presence of a companion star. They may be isolated, grouped in clusters, or so vast that their atmospheric density remains very low, giving their surface the appearance of a gaseous mantle agitated by supersonic winds. The elements they forge travel through the galaxy, mingle with other clouds, and become the building blocks of new planets and, potentially, life. Their winds interact with the interstellar medium, creating arcs and shockwaves, as with Mira, whose leading edge is marked by an ultraviolet structure. The fusion of helium into carbon and oxygen, the convection that brings these elements to the surface, and their dispersion into space constitute one of the most powerful mechanisms of cosmic recycling. By shedding their outer layers, they unveil their incandescent core, initiating the birth of a planetary nebula before ending as white dwarfs. Observing Aldebaran, Mira, or Arcturus is to read in the sky the story of the end of medium stars and the eternal cycle of matter. These red giants announce the end of a cycle, but also the promise of new stars and new planets. They remind us that nothing in the universe is static. Everything transforms. Their glowing red light bears witness to a majestic transition, offering the cosmos the materials that will make possible the birth of future worlds. Thus, their flamboyant twilight is not a mere end. It is a rebirth, where the star returns to the sky, the treasure it has patiently forged. Each red light shining in the firmament is the promise of other suns and other stories. Blue and yellow supergiants rank among the most luminous and massive stars observable in the Milky Way. A star is classified as a supergiant when its initial mass often exceeds 15 times that of the Sun. At this scale, the radiation pressure produced by internal radiation becomes dominant and acts as a powerful energy engine. This intense radiation counteracts the internal gravitational attraction, giving the supergiant its colossal radius and exceptional luminosity. Blue supergiants, just like yellow ones, are distinguished by their impressive size and high surface temperature. That of blue supergiants can reach several tens of thousands of degrees Celsius, while yellow supergiants, more tempered, have surface temperatures around a few thousand degrees. This difference directly influences the perceived color of the photosphere, the superficial layer from which visible light escapes. The hotter blues emit intensely in the ultraviolet and blue. The yellows exhibit a softer glow, close to off-white with golden hues. These titans are born within vast clouds of gas and dust, called nebulae, mainly composed of hydrogen. When some dense regions collapse under their own gravity, they form protostars. If the accumulated mass exceeds 15 solar masses, evolution toward a supergiant becomes inevitable. Unlike lighter stars, which sometimes take tens of millions of years to reach maturity, these future supergiants quickly reach the main sequence stage, where hydrogen fusion fuels their core. Once fusion begins, the star enters a stable phase, but one of short duration on a cosmic scale. The more massive the star, the more rapidly it consumes its nuclear fuel. While a star like the Sun can shine for billions of years, a blue supergiant often fades in just a few million years, a true fleeting flash in the life of a galaxy. The color of a supergiant reflects its surface temperature. The blue ones, hotter, show a spectrum centered on blue and ultraviolet, while the yellow ones, slightly cooler, tend to cream or golden hues. This distinction also relies on spectral analysis, which reveals the chemical composition, stellar winds, and the structure of the surrounding gas. Inside a blue supergiant, the temperature reaches several billion degrees Celsius, favoring the most intense fusion reactions. This energy, combined with sometimes rapid rotation, creates instabilities in the upper layers. Pressure and density waves propagate, creating pulsations on the surface, sometimes called alpha Cygni instabilities, causing slight variations in brightness and spectrum. These oscillations, comparable to waves on a plasma ocean, reflect the internal movements of matter. Astronomers detect them by precisely observing the emitted light and the changes in spectral lines related to the elements present in the atmosphere. Massive supergiants also generate stellar winds of extreme power. Radiation pressure continuously removes enormous amounts of matter, composed of charged particles, escaping at speeds of up to several thousand kilometers per second. This mass loss alters the star's evolution by reducing the fuel available in its deep layers. The initial mass does not solely determine the star's end of life. The cumulative losses during the supergiant phase can considerably reduce its size before its final collapse. Thus, a star of more than 20 solar masses can, after repeated ejections, end its life as a supernova, neutron star, or black hole. These mass losses contribute to galactic feedback, meaning the influence of massive stars on their environment. Stellar winds enrich the interstellar medium with heavy elements, favoring the formation of new stars and planets. They also shape gas clouds, sometimes creating immense bubbles in space. To study the distribution of supergiants, astronomers analyze OB associations, large groupings of hot and massive stars. These clusters, located in the spiral arms of the Milky Way, serve as true laboratories to understand the formation and evolution of high-mass stars. Mapping these associations allows locating areas where the formation of supergiants is intense. Their radiation and winds influence the dynamics of gas clouds over several light years, sometimes triggering the birth of new stars. A yellow supergiant may appear in these associations, often in a transition phase. A blue star may cool slightly, increase its radius, and become temporarily yellow before changing appearance again, depending on the evolution of its fuel. The color thus reflects both temperature and a specific moment in the star's life. Magnetic fields, although less studied than in the case of pulsars, also exist in these giant stars. They can shape the plasma distribution, direct matter ejections, and create circumstellar structures. Rotation, magnetism, and radiation pressure together determine the mass loss and the final shape of the star. Mass ejections produce shells or bubbles of matter, favoring the birth of more modest stars. The ionization of the surrounding gas reveals the chemical composition of the expelled envelopes and the speed of their expansion. At the end of their life, fusion becomes more complex. Hydrogen, helium, carbon, oxygen, neon, then silicon ignite successively, forming concentric layers. The core becomes an iron nucleus, incapable of producing energy. The gravitational collapse that follows leads to a supernova or direct collapse. Among iconic blue supergiants, Rigel shines in Orion. With a mass approximately 20 times that of the Sun and a surface temperature exceeding 10,000 degrees, it emits a brilliant bluish-white light. Deneb in the Swan is also among the brightest stars visible to the naked eye, despite its distance of several thousand light-years. On the yellow side, Ariazi Cassiopeiae stands out for its luminosity variations and colossal size, several hundred times that of the Sun. Its episodes of matter expulsion modify its appearance and contribute to enriching the interstellar medium. Studying these giants reveals the major role of massive stars in recycling galactic matter and forming future stellar generations. Their brightness and explosive or implosive fate bear witness to the perpetual dynamics of the universe and invite continuous observation. Wolf-Rayet stars have captivated astronomers and astrophysics enthusiasts for over a century. To understand this enthusiasm, one must outline the portrait of these exceptional stars. In this narrative journey, we will explore what distinguishes them: stellar winds of extreme intensity, unique spectral signatures, impact on their environment, and on their future evolution. We will also address binarity scenarios, the phase preceding the final explosion, and notable examples such as WR104 and the star Gamma Velorum. Prepare to dive into a universe of unleashed forces and dizzying heat, where some of the heaviest elements in the cosmos are forged. Wolf-Rayet stars are very hot and massive stars that have already passed through several stages of their evolution. They have lost most of their outer layers, exposing areas close to their core. They do not simply radiate, they constantly project enormous amounts of matter through stellar winds that can exceed 2,000 kilometers per second. In 1 second, this matter travels several thousand kilometers in space. The combination of this extreme speed and luminous power makes them privileged objects for studying mass ejection mechanisms and their effects on the interstellar medium. Their discovery dates back to 1867, when Charles Wolf and Georges Rayet at the Paris Observatory detected unprecedented light spectra, intense emission lines instead of the usual absorption lines. These signatures revealed the presence of extremely hot and dense gas escaping at high speed. This type of star quickly took the name of its discoverers. To understand their winds, one must mention radiation pressure, a radiation so intense that it literally pushes the matter outward. Surface temperatures often exceed 25,000 degrees Celsius and can cross 100,000. This energy propels the matter in the form of supersonic flows, mainly composed of ionized particles. These powerful winds strip away almost all the outer layers, leaving only the burning internal regions rich in heavy elements. The luminous spectrum of a Wolf-Rayet tells this story. Emission lines of doubly ionized helium, quadruply ionized carbon, and triply ionized nitrogen. They come from the heated and ionized gas surrounding the star, in a state of strong excitation that re-emits energy in the form of marked spectral lines. This degree of ionization betrays the extreme heat and the fact that hydrogen has disappeared from visible layers, replaced by elements resulting from successive fusion reactions. These supersonic winds enrich the interstellar medium with heavy elements. Over time, carbon, nitrogen, oxygen, and other more massive nuclei mix with the surrounding gas, contributing to the formation of new stars and planets. Without such contributions, our galaxy would be much poorer in materials necessary for complex chemistry and life. The loss of mass is explained by particle kinetics. Each emitted photon transfers part of its momentum to the atoms and ions it encounters, pushing them outward. In Wolf-Rayet stars, instabilities create spiral structures or internal shocks that further heat the material, enhancing the ejection. Many Wolf-Rayet stars are part of binary systems where the winds of two massive stars collide. These shock zones can reach extreme temperatures and emit strongly in X-rays. In some cases, the Wolf-Rayet even transfers mass to its companion, accelerating its own stripping and bringing it more quickly to the pre-supernova phase, often followed by a type IB or IK explosion. BER 104 is a striking example. Its interactions with a companion form a spectacular dust spiral shaped by the periodic encounter of the winds. This structure, observed in infrared, extends and evolves over time and could be disrupted by the future supernova of the star. Another remarkable case, Gamma Velorum, a multiple system comprising a Wolf-Rayet and a blue supergiant. The collision of their winds generates violent shocks, variable X-ray emissions, and arcs of material heated to several million degrees. The study of this system helps refine models of mass loss and wind dynamics. Eventually, these stars unveil layers rich in helium, carbon, and nitrogen. Their evolution often starts like that of a massive O or B-type star. Then the radiation pressure blows off their outer envelope, leaving behind a burning core ready to collapse into a supernova. This process significantly contributes to the chemistry of the universe, as these explosions scatter the elements forged at the heart of the star into space. The expression naked cores comes from the fact that the absence of hydrogen reveals the inner layers. The supersonic winds gradually strip the star, like a sculpture revealing its glowing skeleton. Some Wolf-Rayet stars even generate intense magnetic fields or swirling structures in their winds. The Wolf-Rayet phase, lasting a few 100,000 years, remains short on the cosmic scale, but crucial in the evolution of massive stars. Many supernovae IB and IX would directly come from these stars, even though other scenarios exist. Their study mobilizes all wavelengths: optical for emission lines, ultraviolet for energetic fluxes, infrared for dust, X-rays for shocks. Each domain complements our understanding of their structure and influence. Questions remain about the formation of heavy elements in the deep layers, the effect of convection and rotation, or the impact of the initial metal composition. In metal-poor environments, the Wolf-Rayet phase may appear later or last less time. Numerical simulations today allow modeling of the wind dynamics, binary collisions, and internal chemistry, directly comparing these results to observations. WR-104 notably serves as a laboratory for understanding dust formation in extreme environments, while Gamma Velorum allows analysis of the three-dimensional structure of the winds. The final fate of Wolf-Rayet's stars is almost always explosive. Their supernova leaves a compact object, a neutron star or a black hole, depending on the residual mass. The ejected matter then clumps together, sowing the seeds of new planets. In the vastness of the universe, stars do not always dance alone. Among the most fascinating stellar phenomena are multiple systems and variable stars. The gravitational dance describes the reciprocal influence exerted by 2, 3, or more stars orbiting around a common center of mass. This cosmic ballet takes various forms. Some stars remain distant, while others, the close binaries, exchange matter. Observing and analyzing these stellar assemblies offers a valuable insight into the laws that govern the structure and evolution of stars. Gravitation shapes the birth, life, and sometimes the death of these interdependent stars. Tight binaries orbit so closely to each other that their gravitational fields intertwine. The mutual force can deform their surfaces and create a bridge of matter, allowing the more massive or more voracious star to siphon off its companion. This mass transfer alters each star's evolution. One may become brighter or change spectral type, while the other loses part of its envelope, affecting its stability and lifespan. This tumultuous relationship deeply shapes their destiny. When stars are less close, they may share a circumbinary disk, a ring of gas and dust surrounding the two stars. This disk can give birth to circumbinary planets, evolving in a shifting gravitational field. Stable orbits reveal the flexibility of planetary formation and the complexity of interactions in multiple systems. These configurations are noticeable by the variation in apparent luminosity. Each orbit, each eclipse, or mass transfer influences the light detected from Earth. Studying these variations reveals the mass, size, distance, and presence of additional planets. Modern algorithms and space telescopes can detect these subtle changes. Understanding orbital mechanics and mass distribution enriches our cosmic models and sheds light on stellar physics under extreme conditions. Some variable stars play a crucial role in measuring the universe. Cepheids, pulsing regularly, have a connection between their period and their true luminosity. The longer the period, the brighter the star. This relationship serves as a marker for estimating extragalactic distances. By comparing the observed luminosity to the true luminosity, one determines the distance of the Cepheid and establishes the cosmic scale. Cepheids vary in size and surface temperature, which alters their luminosity and color. Studying their pulsations, sometimes conducted several times per night, refines the period luminosity relationship and helps us understand their internal structure, gas layers, and thermonuclear reactions. RR Lyrae stars, less luminous than Cepheids, display a similar pulsation profile. Their age makes them markers of the oldest stellar populations. They are abundant in globular clusters and provide insights into the evolutionary history of the Milky Way. Thanks to their stable periodicity, they contribute to the scale of intergalactic distances. Combined with Cepheids, they help establish a distance scale ranging from our galaxy to the confines of distant galaxies. RRR. Lyrae stars are used for nearby distances, Cepheids for larger distances. This cross-validation is essential to refine the Hubble constant and better estimate the size and age of the observable universe. Cataclysmic variables offer a spectacular display. A white dwarf attracts matter from a companion star, forming an accretion disk. When pressure and temperature rise, a thermonuclear explosion occurs, causing a brightness surge, the nova. These phenomena, recurrent or unique, are laboratories for studying nuclear physics. In the case of recurrent novae, the white dwarf accumulates material until a new explosion. Each event releases synthesized elements, enriching the galaxy. The frequency and power of these explosions depend on the white dwarf's mass, the accretion rate, and the gas's chemical composition. Studying these cycles illuminates the evolution of binary systems and their role in galactic chemistry. Sometimes, the accumulation of matter triggers a type Ia supernova. The incredibly bright explosion releases a wide range of elements, and its relatively uniform intrinsic luminosity allows for the measurement of large cosmic distances. The study of cataclysmic systems and their precursors is essential to modern cosmology. The observation of these events has allowed us to map the universe and understand cosmic expansion. Each flare provides clues about the mass, composition, and environment of the stars. Historical surveys and automated monitoring programs accelerate the detection of these phenomena. The spectra obtained before, during, and after the explosion reveal the evolution of temperature, shock waves, and star chemistry. Each detail refines theoretical models and distance estimates. Variable stars also allow us to measure time in the universe. Period variations provide information about internal structure or the presence of an invisible companion. In eclipsing binaries, precise monitoring of orbital passages reveals orbital evolution, gravitational perturbations, and energy loss through gravitational waves. These observations illuminate stellar physics and general relativity while contributing on a cosmic scale. Modern techniques and telescope networks ensure almost continuous monitoring. Real-time alerts enable rapid targeting of instruments on a phenomenon. Interferometry, photometry, and spectroscopy provide information on the structure and dynamics of celestial bodies. Spectral analysis detects gas movements at several hundred kilometers per second and reveals their composition. Each instrumental advancement refines the understanding of the gravitational dance of multiple systems. The study of these multiple systems and variable stars advances our understanding of gravity, stellar physics, and cosmic dynamics. Their observation, from visible wavelengths to infrared and radio waves, reveals the richness of processes. Each eclipse, burst, and pulsation sheds light on stellar evolution and the methods of measuring distance and time. Tight binaries demonstrate the sharing of matter and the limits of stability. Cepheids and RR Lyrae trace the cosmic geography, while cataclysmic variables remind us of the power of fusion under the effect of gravity. At the twilight of their existence, some stars leave behind fascinating remnants that challenge our understanding and reveal laws of matter under extreme conditions. We will explore 3 of these relics: white dwarfs, pulsars, and magnetars. Their origin traces back to the point where the star, having exhausted its nuclear fuel, can no longer maintain its internal balance. The end is sometimes spectacular, sometimes more discreet, but always marked by an extraordinary density. Stars of moderate mass become white dwarfs, supported by electron degeneracy pressure. The more massive ones collapse into neutron stars, even denser, some of which manifest as pulsars or magnetars. The latter highlight the extreme effects of rapid rotation and colossal magnetism. This journey will plunge us into the heart of mechanisms that counteract gravitational collapse and the ensuing phenomena. White dwarfs, the ultimate stage of low or medium mass stars, appear when nuclear fusion ceases in their core. The star then expels its outer layers, revealing a hot and dense core. This core remains stable thanks to quantum mechanics, which imposes that electrons cannot share the same energy state. This principle limits matter compression and preserves the star's structure. Nonetheless, the density is such that a teaspoonful of this matter would weigh several tons on Earth. White dwarfs start at temperatures exceeding 100,000 degrees, then cool slowly over billions of years. Their size is similar to that of Earth, but their mass approaches that of the Sun, resulting in a vertiginous surface gravity. When the mass of the dying star exceeds a certain threshold, electron degeneracy pressure is no longer sufficient. The collapse continues, fusing protons and electrons into neutrons. The result is an extremely dense neutron star, a few tens of kilometers in diameter, with a mass similar to or greater than the Sun. Neutron degeneracy pressure, also of quantum origin, counterbalances gravity. By conserving angular momentum, these stars rotate rapidly, and in the case of pulsars, their rotation is accompanied by an intense magnetic field and electromagnetic beams that sweep through space like a lighthouse. When one of these beams crosses Earth, we perceive a regular pulse, crucial for time measurement and space navigation. Some pulsars reach a rotation speed of several hundred revolutions per second. They are called millisecond pulsars. Their already powerful magnetic field generates impressive radio and sometimes X-ray emissions. But magnetars exceed even these records. Their magnetic field reaches up to 10 to the power of 15 Gauss, capable of influencing the star's internal structure and generating colossal stresses. When these stresses are released, they cause soft gamma-ray bursts, detectable over great distances. These phenomena make magnetars genuine natural laboratories for studying the effects of extreme magnetism. The most violent eruptions of magnetars release phenomenal energy in a few seconds, altering the spatial environment at considerable distances. Their regular emission of X-rays and gamma rays, combined with a magnetic field capable of altering atomic structure, makes them unique subjects for nuclear physics and general relativity studies. Their extreme gravity, concentrated in a tiny volume, tests our models of strong gravity. In their core, the density is such that neutrons could break up into quarks, opening new perspectives on the fundamental structure of matter. Their envelope, sometimes superfluid, can cause sudden rotational changes called glitches, valuable clues to their internal composition. Regular observation of these phenomena refines our equations of state, the formulas that link pressure, density, and temperature. To study them, astronomers use radio telescopes and space-based X-ray and gamma-ray telescopes, capable of capturing signals from these compact stars. Pulsars are identifiable by their regular radio pulses, while magnetars reveal themselves through their unpredictable bursts. Gravitational astronomy complements these observations, offering a fresh look at the internal vibrations of these stars. Future generations of detectors should allow even finer exploration of their dynamics. In parallel, theoreticians refine their models. For white dwarfs, they study the gradual crystallization of their core, which changes their luminosity and slows their cooling. For neutron stars, they try to determine if some cross the limit towards quark stars, even more compact. Magnetars, with their titanic fields, could harbor exotic states of matter, mixing superconductivity and superfluidity. Every measurement of mass, radius, rotation, or magnetic field refines our understanding of fundamental laws. Thus, white dwarfs, pulsars, and magnetars embody three aspects of extreme density and energy. Together, they influence their galactic environment and enrich the interstellar medium. The formation of a stellar black hole is both a fascinating and mysterious astrophysical phenomenon. Imagine a massive star, much heavier than the Sun. For millions of years, it burns its hydrogen and then its helium, gradually forming layers of heavier elements at its core. When its nuclear fuel is exhausted, the radiation pressure is no longer enough to counteract gravity. Then begins a cataclysmic collapse that can lead to the birth of a black hole. For such an object to form, the residual core must exceed about 3 times the mass of the Sun. Beyond that, no internal force can prevent the matter from contracting to almost infinite density. The Schwarzschild radius defines the boundary beyond which nothing, not even light, can escape. Crossing this horizon marks a point of no return. Some black holes, spinning rapidly, possess an area called the ergosphere. Their rotation distorts and drags the surrounding space, forcing any particle to follow this motion. This region could, under certain conditions, allow the extraction of some of the black hole's rotational energy, although the mechanism remains debated. After the formation of a black hole, the surrounding matter does not disappear immediately. Gas and dust from the collapsed star or neighboring stars can form an accretion disk. This swirling structure heats to several million degrees, emitting intense X-rays. The gravity is so extreme that even the slightest disturbance causes spectacular effects. In some cases, this disk generates relativistic jets, powerful flows of particles ejected at high speed along the poles. Their exact origin is still being studied, but an intense magnetic field seems to channel their formation. These jets appear notably in microquasars, miniature versions of giant quasars. Microquasars often manifest through transient X-ray emissions, alternating between intense phases and calm periods. During bursts, the disk releases a colossal amount of energy, then cools down as the supply of matter decreases. Real-time observations have made it possible to track these variations and better understand their dynamics. A major breakthrough came from the detection of gravitational waves, those deformations of space predicted by Einstein. They are born during the merger of two compact objects. In 2015, the LIGO, Virgo, and Cagra observatories recorded for the first time a signal from the coalescence of two massive black holes. These mergers produce brief but powerful bursts of gravitational waves. Their analysis reveals the mass, rotation, and history of the objects involved, while testing general relativity under extreme conditions. When a stellar black hole is born from a supernova, the explosion disperses heavy elements like iron or nickel into space. The accretion disk can also, under extreme temperatures, forge rare atomic nuclei that then propagate into the cosmos. These environments, with a density and pressure comparable to those of stellar cores, promote nuclear reactions capable of producing gold, platinum, or other heavy metals. The study of the light emitted by these ejections allows astrophysicists to trace the origin of these precious elements. Direct observations of these disks and jets sometimes reveal unusual chemical signatures, signs of exotic nuclei. Each discovery enriches our understanding of the link between black hole activity and the composition of the universe. Different types of black holes are distinguished: supermassive at the centers of galaxies, intermediate, and stellar, the latter having a mass a few times that of the Sun. Their small size does not prevent them from being observed in full activity, revealing phenomena occurring on human timescales. The detection of a black hole often relies on the study of a stellar companion. A star orbiting around an invisible object, too massive to be a normal star, is a strong clue. X-ray emissions, or the appearance of jets, confirm the presence of an accretion disk. Another method, gravitational lensing, where an invisible object temporarily amplifies the light of a distant source. This phenomenon could reveal the existence of isolated black holes, although the required precision makes observation difficult. Detection technologies are rapidly advancing. Next-generation interferometers promise to capture lighter or more distant mergers, while automated surveys multiply the discoveries of high-energy objects. The theoretical modeling of these phenomena requires complex calculations integrating general relativity, plasma physics, and rotation effects. Numerical simulations are becoming increasingly precise, directly confronting predictions and observations. Studying these objects allows testing gravity under extreme conditions. A divergence between observations and Einstein's predictions could revolutionize current physics, but for now, the theory holds. Multi-messenger astronomy, combining electromagnetic signals and gravitational waves, offers a more comprehensive portrait of black holes. A simultaneous detection of gamma rays and gravitational waves, for example, would allow the study of the creation of heavy elements in gas-rich environments. These researches are part of a larger quest to understand the birth, life, and death of stars. Black holes influence stellar formation, the distribution of elements, and the chemical evolution of galaxies. For us, they remain vertiginous enigmas, proof that the universe harbors realities defying our intuition. From the first theory in the 19th century to recent observations, each advance raises new questions. Perhaps they are not only the end of stars, but also engines of cosmic change. In the vastness of our galaxy, a constant ballet of celestial events illuminates space, sometimes beyond all imagination. The 11th stage of our journey takes us to the heart of transient phenomena and exotic objects: supernova, kilonova, quark stars, and other hypotheses from the frontiers of theory. Each of these brief and intense events offers the discerning observer precious clues about the evolution of stars. Here, we will explore their nature to better understand what they reveal about the universe. In astronomy, a transient phenomenon refers to an event of short duration on a cosmic scale. Compared to the life of an average star, which can last billions of years, these manifestations appear as fleeting flashes, sometimes a few days, sometimes only a few hours. Yet, they unveil great mysteries. The final explosion of a massive star, the fusion of two dense stars, or the collapse into unknown states of matter. In this immense cosmic symphony, every flash is a precious note for reconstructing stellar history. Among these manifestations, supernovae are the most spectacular. This term refers to the terminal explosion of a star. There are several types, classified according to their mechanism and spectral signature. Type 2 supernovae occur when a massive star, having exhausted its fuel, can no longer resist gravity. Its core collapses, the outer layers rebound, projecting light and matter into space. Type Eb and Ik supernovae experience the same violent end, but their envelope differs. In the former, hydrogen has disappeared. In the latter, hydrogen and helium have almost entirely been lost, leaving a bare core. These cases often involve Wolf-Rayet stars, known for their intense stellar winds. The explosion then reveals a glowing core and scatters enormous quantities of debris. These explosions are not just a luminous spectacle, they forge and disperse heavy elements like nickel, cobalt, and gold into space, which will enrich interstellar clouds. New stars and planets will form from this material, and every oxygen or carbon atom we carry might come from the blazing death of a massive star. Even rarer, kilonovae result from the fusion of two neutron stars. These tiny but dense stars concentrate more mass than the Sun in just a few tens of kilometers, gradually drawing closer due to gravitational waves until they collide. The resulting explosion shines 1,000 times brighter than a classical nova, but quickly fades. These events are essential for understanding the formation of the heaviest elements: gold, platinum, uranium. They confirm the role of the rapid neutron capture process and enrich our vision of cosmic chemistry. They have also marked the history of gravitational wave detection. Observing both light and space-time vibrations simultaneously has opened a new era for astronomy. Beyond the observed phenomena, some hypotheses push the limits of known physics. Quark stars might form if the pressure at the core of a neutron star breaks neutrons into free quarks, creating what is known as deconfined matter. Boson stars, meanwhile, would be composed of particles obeying different quantum laws, possibly linked to dark matter. These ideas, still theoretical, fuel research and could revolutionize our understanding of matter. The study of these phenomena relies on increasingly sophisticated instruments, space telescopes, gravitational wave detectors, multi-wavelength analysis, and soon, the observation of light polarization. Neutrinos, nearly elusive particles, offer another key. They carry the signature of deep processes occurring at the heart of explosions. On Earth, alert networks and automated telescopes continuously scan the sky, instantly triggering an observation campaign when a suspicious flash appears. Tomorrow, new, more sensitive lunar or terrestrial observatories will allow us to detect these fleeting bursts even earlier. Each discovery pushes back our certainties. After having long believed that supernovae represented the pinnacle of stellar end of life, we discovered kilonovae, then considered even stranger objects. This diversity illustrates the richness and violence of cosmic transformations. Supernovae, revealing the end of massive stars; kilonovae, unveiling the creation of heavy elements and hypothetical stars, brushing the boundary of speculative physics. The future of astronomy will be played out in these extremes, detecting faster, analyzing more finely, understanding more deeply. Each observation is an invitation to push the boundaries of knowledge further, to listen to the story the universe whispers to us through its lights and waves. In this endless journey, each star explosion is both an end and a beginning. The death of a star can sow the seeds of new stars, new planets, and perhaps, elsewhere, new forms of life. The exploration continues, driven by our instruments, our imagination, and our thirst to understand. O and B-type stars form a class apart in the stellar bestiary. They do not resemble our sun, nor even its cooler or more discreet neighbors. They embody excess, extravagance, and fleetingness. For they are born massive and radiant, live fast and die young, leaving behind cataclysmic explosions and chemical legacies that shape the universe. O-type stars are the most extreme of this family. They are born in giant molecular clouds, these vast expanses of gas and dust where gravity gathers pockets of matter. For such a star to form, the collapse of the cloud must accumulate a colossal mass, exceeding 15 times the mass of the sun, and can climb up to 100 solar masses, or even more in some exceptional cases. From their birth, they reach frightful temperatures, between 30,000 and 50,000 degrees Celsius on the surface. For comparison, our sun displays only 5,800 degrees. To the human eye, if we could see them without a filter, they would appear a dazzling blue, almost otherworldly, because their spectrum is dominated by ultraviolet and the ionization of helium. This heat and mass translate into a luminosity beyond compare with that of a solar-type star. A single O star can shine as brightly as several 100,000 suns combined. It emits a constant shower of high-energy photons that flood its environment. This radiation is so powerful that it doesn't just illuminate, it shapes the surrounding matter. In the nebulae where they are born, O stars create immense bubbles of ionized gas, sculpting brilliant cavities that we observe with our telescopes. The Orion Nebula, for example, is illuminated by such stars. They give these clouds their ghostly glow and spectacular structure. But this power comes at a price. O stars burn their nuclear fuel at a dizzying speed. In their core, hydrogen fuses into helium at such a rapid pace that their lifespan is counted not in billions of years like our sun, but in just a few million. Their existence is thus brief on a cosmic scale. They appear, blaze intensely, then die, leaving an indelible imprint on their environment. Their end is almost always spectacular: titanic supernovae, hypernovae, or even direct collapses into stellar black holes. Thus, each O star can be seen as a cosmic fireworks, as swift as it is gigantic. B-type stars are their less extreme younger siblings, but just as impressive to a terrestrial observer. Their mass varies between 2 and 16 times that of the sun, and their surface temperature oscillates between 10,000 and 30,000 degrees Celsius. They shine a bluish white, less intense than the O stars, but still well beyond what we know with our sun. They too were born in regions of star formation, often in association with other massive stars. Their light is sufficient to ionize the surrounding nebulae, transforming them into true cosmic beacons. B stars live longer than O stars, but their lifespan is still limited to a few tens or hundreds of millions of years, a blink of an eye on the galaxy scale. Rigel in the constellation Orion is the most striking example. Now classified as a blue supergiant, it was once a type B star when it was still on the main sequence. Its brightness dominates Orion and illuminates the neighboring gas clouds. To the naked eye, it far surpasses most stars in the sky, even though it is more than 800 light-years away. Its light, traveling at the prodigious speed of 300,000 kilometers per second, thus takes 8 centuries to reach us. Observing Rigel is observing the deep past, contemplating a star that began to shine intensely long before the birth of our civilizations. In the heart of an O or B star, physics is pushed to its limits. Gravity, which tends to crush the star upon itself, is counterbalanced by radiation pressure and the energy released by nuclear fusion. The more massive the star, the stronger its gravity, and the more intense the fusion must be to maintain equilibrium. This unstable balance explains why massive stars consume their hydrogen so quickly. Gravity demands a colossal firepower, and the star responds by burning its fuel without restraint. The nuclear fusion chains occurring in these stars, notably the carbon-nitrogen-oxygen (CNO) cycle, dominate their energy production. Unlike the Sun, which primarily uses the proton-proton chain, O and B stars derive their energy from a more efficient, but also more demanding mechanism, which only operates at extremely high temperatures. The radiation from these stars doesn't just produce light, it literally strips matter from their surface. The stellar winds of O and B stars are of unimaginable violence. Jets of ionized plasma erupt at speeds of several thousand kilometers per second. In a single year, an O star can lose as much mass as the entire Earth, or even more. Over its lifetime, it can shed several dozens of solar masses, radically transforming its future evolution. These stellar winds also create bubbles of hot gas in the interstellar medium and contribute to a process called stellar feedback, the influence exerted by massive stars on their environment, sometimes stimulating the formation of new generations of stars and dispersing or compressing molecular clouds. These massive stars are rare. In our galaxy, for several 100 million stars similar to the Sun, there are only a handful of O stars. B stars are a bit more numerous, but they remain a minority compared to red dwarfs, which largely dominate in quantity. However, it is they, the O and B stars, that dictate the rhythm of galactic evolution. Their light, their winds, their explosions shape the cosmic landscape far more than the myriad of modest stars. Without them, the heavy elements essential to life, carbon, oxygen, iron, calcium, would never have been produced in sufficient quantities. We ourselves, made of atoms forged in the hearts of stars, carry within us the legacy of these titans long gone. The OB associations, massive groups of young, massive stars, are among the most fascinating structures in the sky. In these groups, dozens of O and B stars are born almost simultaneously in a giant gas cloud. Their intense light ionizes the remaining gas, creating HHII regions that are bright and visible over dozens or even hundreds of light years. These regions are the stellar nurseries of the galaxy, but they are also ephemeral. After a few million years, the most massive stars explode as supernovae, dispersing the cloud that gave them birth. The stellar formation cycle then continues elsewhere, fueled by the enriched materials released by these explosions. Zeta Puppis, an isolated and bright O star, well illustrates the power of these stars. Located about 1,000 light-years away, it shines with such intensity that it is visible to the naked eye despite its distance. Its stellar winds are so strong that they generate shock waves in the surrounding gas, observable in X-rays. This star, like many of its counterparts, will end its life in a titanic explosion, possibly leaving behind a black hole. Each O star is a cosmic time bomb, a countdown played out over a few million years. Among the vast family of stars, some stand out for their particular brilliance, visible even to the naked eye and often associated with the most famous constellations. They are neither as colossal and violent as type O and B stars, nor as modest and discreet as the countless red dwarfs that populate the galaxy. They occupy an intermediate position, where their mass, temperature, and luminosity allow them to stand out with a simple and striking beauty. These are type A stars, with a slightly bluish-white color, true luminous beacons of our night sky. In parallel, at the other end of the life cycle, are far more discreet but fascinating stars by their nature, subdwarfs, often designated by the letters SDO, SDB, or SDM. These older and more exotic objects do not shine through their brilliance to the naked eye, but through the secrets they reveal to astronomers, particularly about the end of life of intermediate stars. Type A stars have surface temperatures ranging between 7,500 and 10,000 degrees Celsius. For comparison, our Sun, a type G star, reaches only about 5,800 degrees. This temperature difference gives type A stars their characteristic color, a dazzling white sometimes tinged with blue, which contrasts markedly with cooler stars leaning towards yellow or orange. Their spectrum, meaning the luminous signature obtained by decomposing their radiation, is dominated by strong hydrogen absorption lines, allowing astronomers to quickly identify them. Their mass, generally between 1.5 to 3 times that of the Sun, grants them much more energy than solar-type stars, but this abundance of energy translates to a faster consumption of their nuclear fuel. Where the Sun can live for about 10 billion years, type A stars only shine for between a few hundred million and about 1 billion years. They are, on a cosmic scale, young and fleeting stars. One of the most famous examples of a type A star is Sirius, the brightest star in the night sky. Located about 8 light-years from us, it dominates the constellation of the Great Dog, and has been observed by human civilizations for millennia. Its brightness is such that it has inspired myths and legends across several continents. In reality, Sirius is a binary system. Next to the main star, Sirius A, there is a white dwarf called Sirius B, the remnant of an ancient star. Sirius A, the type A star, shines with a brilliance about 25 times that of the Sun and has a mass twice as large. Its light, white and pure, perfectly illustrates the class of A stars. Its lifespan will be short, and in just a few 100 million years, it will leave the main sequence to evolve into a red giant, then a white dwarf, like so many other intermediate mass stars. Another striking example is Vega, in the constellation Lyra. Vega is one of the most studied stars in the sky, as it has long served as a reference for calibrating astronomers' luminosity scales. Located 25 light-years from us, it shines with an intensity 40 times that of the Sun. It has an interesting feature. It rotates extremely fast on its axis. Its rotation period is less than a day, resulting in a noticeable flattening at its poles. This rapid rotation alters its internal structure and radiation, characteristics that make it a natural laboratory for understanding the influence of stellar rotation. Its white, slightly bluish light is a true signature of the type A. Vega, like Sirius, is only at the beginning of its stellar life. In about 500 million years, it too will begin its transformation into a red giant. Type A stars also play an essential role in celestial mapping and human navigation. Many of them are visible to the naked eye and serve as landmarks in constellations. The nebula, for example, in the constellation of Leo, marks the tail of the animal in celestial representations. With a mass about twice that of the Sun and a luminosity 12 times greater, it again illustrates the power and relative youth of A-type stars. Although less bright than Sirius or Vega, it remains clearly visible and serves as a reference in its part of the sky. Thus, these stars, by their visibility and brilliance, occupy a particular place in our perception of the universe. They embody a category that lies between ephemeral giants and small, discrete stars, a sort of middle ground that naturally attracts the human eye. Scientifically, A-type stars present a particular interest for the study of planetary formation. Their lifespan, although shorter than that of type G or K stars, is still sufficient for planets to form around them. Protoplanetary disks have been detected around some A stars, and it is suspected that rocky worlds like Earth could exist in these environments. However, their intense ultraviolet radiation and sometimes high activity can complicate the emergence and stability of atmospheres conducive to life. Astronomers therefore carefully study these systems to understand the conditions under which life might appear elsewhere than on Earth. Vega is a particularly telling example. Its debris disk, composed of dust and rocks, shows signs of organization reminiscent of the early stages of planetary formation observed around other stars. Beyond the A stars themselves, another group of celestial bodies attracts the attention of astrophysicists, the subdwarfs. Unlike A stars, young and bright, subdwarfs are old stars, often resulting from complex evolutions or interactions with a binary companion. They do not shine by their visible luminosity, but by the richness of their history and the enigmas they allow to solve about the fate of stars. Subdwarfs are classified into several types, according to their composition and temperature, SDO, SDB, and SDM. These celestial bodies often have a reduced mass, close to half that of the Sun, but their temperature can be extraordinarily high, between 20,000 and 40,000 degrees Celsius for SDO and SDB. Their brightness comes from a thin, burning envelope, the result of internal nuclear processes that differ from those of main sequence stars. Hot subdwarfs, particularly SDB, are often studied for their pulsations. Some vibrate regularly, much like a cosmic musical instrument. These oscillations translate into luminosity variations that astronomers can measure with precision. By analyzing these vibrations, it is possible to probe the interior of the star, estimate the composition of its core, and better understand stellar physics. Figge 48, a well-known SDB star, is an example of this type of object. Located several hundred light-years away, it offers a valuable laboratory for specialists in astroseismology, the science that studies star vibrations. Thanks to such objects, we refine our models of stellar evolution and better understand what happens to intermediate stars after they leave the main sequence. Subdwarfs do not form in isolation. Often, they are the product of interaction in a binary system. When a star loses a large part of its envelope, sometimes stripped away by a gravitational companion, it can end up reduced to a burning core with a thin hydrogen layer. This residue remains stable for a certain period, producing intense ultraviolet light, but not durable. Thus, subdwarfs testify to a history of violence and loss. They are the incandescent memory of a star that was once much more massive and stable. Their existence allows astrophysicists to better understand the role of binary interactions in the evolution of stellar populations. In the vast menagerie of stars, some defy imagination with their size, brightness, and instability. These are cosmic monsters, titans of fire whose mass sometimes exceeds 100 times that of our sun, and whose luminosity rivals that of hundreds of thousands of ordinary stars combined. These celestial bodies, known as hypergiants, live on the edge of what nature permits. Their existence is a constant struggle against gravity, which tends to crush them, and against radiation pressure, which seeks to tear them apart from within. They are rare, ephemeral, and spectacular. Their instability drives them to expel vast amounts of matter in cataclysmic eruptions that illuminate the interstellar sky and deeply mark their surroundings. Among them, Eta Carinae remains the most famous example, known for its 19th century Great Eruption, an explosion so violent that it transformed an invisible star to the naked eye into one of the brightest celestial beacons in the night sky. To understand the nature of hypergiants, we must go back to their birth. They emerge in the densest regions of giant molecular clouds, where gravitational collapse accumulates colossal masses of gas and dust. While most stars are born with masses lower than the sun, a tiny minority reaches extreme values, sometimes exceeding 100 solar masses. These conditions are so rare that, in a galaxy of several hundred billion stars, only a few dozen hypergiants are known. From their birth, they radiate with prodigious intensity. Their surface temperature often reaches several tens of thousands of degrees, and their light, rich in ultraviolet, ionizes the surrounding gas, creating immense glowing bubbles. Their brilliance is such that it helps sculpt the surrounding gas clouds and triggers the birth of new stars. But this gigantism comes at a price. A hypergiant consumes its hydrogen at a frantic pace, much faster than ordinary stars. Where the sun can live for 10 billion years, a hypergiant exhausts itself in just a few million years. Its life is a luminous sprint toward an inevitable end. Inside, nuclear fusion is at its peak. First hydrogen into helium, then helium into carbon and oxygen, and quickly the heavier reactions. The star knows no respite. Every time a fuel is exhausted, it moves on to the next, in a succession of ever shorter phases. The internal structure of the hypergiant resembles a giant onion, where each layer fuses a different element, from the lightest on the outside to iron at the core. But when iron appears, everything stops, as its fusion no longer releases energy. The core becomes unstable and prepares for collapse. While waiting for this tragic end, the hypergiant battles against its own excesses. The radiation pressure, produced by the colossal amount of photons escaping from its core, tends to push back the outer layers. If this pressure becomes too strong, it literally tears away entire sections of the stellar atmosphere. The mass losses are immense. Tens of solar masses can be expelled during the star's lifetime, forming spectacular circumstellar nebulae. Eta Carinae, for example, expelled the equivalent of several suns of matter during its great eruption in just a few decades. This matter, projected into space, today forms the Homunculus Nebula, two bright lobes extending around the star and bearing witness to the violence of the instabilities that agitate these giants. Hypergiants are so unstable that their luminosity varies, sometimes unpredictably. Some experience phases of relative calm, followed by periods of massive eruptions. These changes are explained by the delicate interaction between gravity, radiation pressure, and internal convection. When the balance is broken, entire layers can collapse inward or, on the contrary, be violently expelled. The variations observed in their brightness are signs of this ongoing internal struggle. For astronomers, these stars are true living laboratories where the laws of physics are tested under extreme conditions. They allow us to test our models of stellar stability and explain the mechanisms that lead to some of the most powerful explosions in the universe, hypernovae. A hypernova is an exceptionally violent supernova resulting from the collapse of a hypermassive star. The energy released exceeds that of classical supernova and can give rise to spectacular phenomena like long-duration gamma-ray bursts. These bursts of energy, observed billions of light years away, could originate from the explosive death of hypergiants. Thus, behind the beauty of these stars lies a potential for destruction and creation on a cosmic scale. For when the hypergiant explodes, it disperses into space the heavy elements it has forged during its life: carbon, oxygen, magnesium, silicon, and up to iron. These elements, scattered in the interstellar medium, enrich future generations of stars and planets. Each explosion marks a step in the chemical evolution of the galaxy, and without these unstable giants, life as we know it would not exist. If hypergiants embody excess and violence, another type of star tells a different but equally fascinating story: helium stars. These stars no longer have their outer hydrogen shell. They are bared stars, revealing deep layers usually hidden in ordinary stars. Their surface temperature can reach 100,000 degrees Celsius, far beyond most other visible stars. Their spectrum is dominated by helium and carbon lines, evidence of the fusion continuing in their core. Some of them are intermediate stages before becoming Wolf-Rayet stars, known for their extreme stellar winds, but others can remain stable for a time, forming a separate, rare, and intriguing class. The loss of the hydrogen shell can occur in several ways. Sometimes, the star expels it itself through intense stellar winds, when radiation pressure exceeds the gravitational forces holding its atmosphere. In other cases, the loss results from an interaction with a companion star in a binary system. The hydrogen is then literally stripped away and transferred to the companion, leaving behind a blazing core where helium dominates. This process radically transforms the appearance of the star. Instead of a familiar yellow or white light, a bluish or ultraviolet glow is observed, invisible to the human eye but detectable by our instruments. These naked stars are precious witnesses to stellar evolution, as they reveal what happens at the core of giants after they have lost their outer layer. HD 45166 is a particularly fascinating example of a helium star. It has an intense magnetic field, making it a magnetic helium star. This field influences the structure of its stellar winds and alters the distribution of its atmosphere. Studying it helps us better understand the role of magnetic fields in massive stars, a still poorly understood area. These stars also highlight the link between stellar evolution and binary systems, as many of them result from interactions with an invisible companion. Their rarity and diversity make them prime objects of study, capable of challenging our traditional models of star formation and death. Helium stars also pose a fundamental question. What do they become? Some continue their evolution towards the Wolf-Rayet state, with increasingly intense winds that will eventually strip the star down to its carbon and oxygen core. Others may explode in particular supernovae, leaving behind a neutron star or a black hole. Their fate depends on their initial mass, composition, and interactions with their environment. In any case, they represent a key step in the life cycle of massive stars and an essential milestone for understanding the diversity of cosmic explosions we observe. Before becoming stable suns, stars undergo a long period of cosmic gestation, hidden in the dark folds of giant molecular clouds. These clouds, made of gas and dust, appear in the sky as opaque nebulas that block the light of stars located behind them. It is in these icy cocoons, only tens of degrees above absolute zero, that the most extraordinary process in the universe occurs, the formation of stars. Everything begins with a gravitational collapse. The gas, primarily composed of hydrogen and helium, undergoes instability. This can be triggered by an external event, such as the shockwave of a nearby supernova, the collision of two clouds, or compression due to galactic rotation. Under the effect of gravity, certain regions of the cloud become denser and start to contract. These dense cores fragment, giving birth to multiple condensations, each of which will be a seed of a star. This is the first stage of protostars, celestial bodies in gestation still incapable of shining by nuclear fusion. In this phase, the protostar is deeply buried in its dust cocoon. The temperature of its core rises gradually, but it remains too low to initiate hydrogen fusion reactions. It radiates primarily in the infrared, as the surrounding dust absorbs visible light and re-emits it as heat. For an Earth observer, these objects remain invisible in optics, but infrared telescopes reveal their presence by diffuse glows. This radiation betrays the process of gravitational contraction. The energy released comes solely from the falling matter towards the center. The more the cloud collapses, the more the protostar densifies and warms up. Around the protostar, a disk forms. Indeed, the collapsing gas retains its angular momentum, which prevents all the matter from falling directly onto the center. It flattens into a rotating disk, much like water swirling down a drain. This protoplanetary disk is not just a side effect. It will be the matrix where future planets, moons, and asteroids will be born. Already, clumps of dust are agglomerating, beginning a long chain of collisions that will lead from grains of a few micrometers to bodies of several kilometers. Thus, while the star grows in mass, its planetary retinue begins to take shape in the secrecy of this disk. As the protostar gains density, it enters a more turbulent phase, the T Tauri stars, if their mass is comparable to that of the Sun. These young stars, only a few million years old, have not yet reached the stable equilibrium of the main sequence. Their luminosity varies chaotically, as their surface is agitated by powerful eruptions, and their magnetic fields trigger bursts of energy. Their stellar winds, much more intense than those of adult stars, blow continuously and interact with the protoplanetary disk. Jets of matter, called bipolar jets, sometimes gush from the poles of the star, extending over several light years and illuminating the surrounding gas. These jets are spectacular signatures of stellar youth. The T Tauri stars are named after their prototype, T Tauri, located in the constellation Taurus. It is a very studied star, as it perfectly illustrates this tumultuous phase. Around it, a disk of dust and gas is still visible, and clear signs of planetary formation have been observed. The variations in luminosity of T Tauri remind us that these stars are unstable, subject to rapid changes in their immediate environment. For astronomers, they represent a precious window into the past of our own Sun, which also went through a T Tauri phase about 4.6 billion years ago. It is in this context that Earth and the other planets of the solar system were formed. When the mass of the forming star is higher, between 2 and 8 times that of the Sun, they are called Herbig AB stars. They are the equivalent of T Tauri stars, but in a higher mass range. Hotter and more luminous, they sometimes ionize the surrounding gas, creating bright nebulae that betray their presence. They are often observed in large star-forming regions like the Orion or Carina Nebula, where myriads of stars are born in clusters. These young stars also possess circumstellar disks, and some already show complex structures, suggesting the emergence of giant planets. Their intense radiation strongly influences the dynamics of their disk, perhaps accelerating the process of planetary formation. The stars we know today, whether they are similar to the Sun, red giants, supergiants, white dwarfs, or neutron stars, all belong to a universe already rich in heavy elements. In their atmosphere, in their spectrum, we find carbon, oxygen, nitrogen, iron, silicon, and many other metals. These elements did not appear with the Big Bang. When the universe was formed, it only produced the simplest building blocks: hydrogen, a little helium, and tiny traces of lithium. No carbon, no oxygen, no iron existed then. This means that the very first stars in cosmic history, the so-called population 3 stars, were radically different from all those we see today. These primordial stars had only hydrogen and helium at their disposal, a stellar chemistry devoid of any metal, and they were the true original forges of heavy elements. The very idea of their existence is based on simple reasoning. If the first stars had not yet produced metals, they must have surely consisted only of the elements that emerged from the Big Bang. Their direct observation remains out of our reach, as they died more than 13 billion years ago. But their descendants, the ancient galaxies we observe through telescopes, still bear the imprint of their passage. Population 3 stars were likely very massive, much more so than most stars today. Simulations suggest they easily reached 100 times the mass of the Sun, sometimes more. Their colossal mass is explained by the absence of metals in their composition. In present-day clouds, heavy elements allow the gas to cool efficiently, favoring the fragmentation of the cloud into small stars. But in the primordial universe, the gas could only cool with difficulty, which led to the formation of more massive blocks of matter. These blocks gave birth to gigantic stars, true luminous monsters. The life of these stars was brief. Their enormous mass doomed them to burn through their nuclear fuel at a blistering speed. Where the Sun will live for 10 billion years, a population 3 star of 100 solar masses would extinguish in less than 2 million years. They were therefore fleeting, but their role was crucial. By exploding in titanic supernovae, they scattered the first heavy elements into the cosmos: carbon, oxygen, magnesium, silicon. These materials enriched the interstellar gas and allowed subsequent generations of stars, known as population 2, to form with more varied chemistry. Every rocky planet, every biological molecule that exists today finds its origin in the work of these vanished stars. We are literally the children of these extinct giants, for without them, the universe would have been nothing but an ocean of hydrogen and helium. Even though they remain invisible, astronomers are trying to detect their indirect imprint. For instance, they are searching for extremely distant galaxies whose light has reached us after more than 13 billion years of travel. These galaxies might still harbor the trace of population 3 stars through their specific spectral signatures. Similarly, some extremely bright supernovae observed in the ancient universe might be the final explosions of these primordial stars. Next-generation telescopes, like the James Webb Space Telescope, are precisely tasked with exploring this distant epoch and perhaps catching the first glimmer of these vanished suns. Beside these real but disappeared stars, theoretical physics has imagined the existence of other, even more exotic types of celestial bodies that push the limits of our understanding. Some of these hypotheses arise from the curiosity of physicists who seek to understand how matter would behave under extreme conditions. Others directly result from the equations of quantum physics or general relativity. These hypothetical stars have never been observed, but they serve as conceptual laboratories to test the coherence of our models. Among them are quark stars, boson stars, and dark matter stars. A quark star would be an even more extreme stage than a neutron star. In a neutron star, matter is compressed to the point where electrons and protons combine to form a soup of neutrons. The density is such that a piece the size of a sugar cube would weigh billions of tons. But some physicists believe that if the pressure is even more intense, the neutrons themselves could deconstruct into their fundamental constituents, quarks. We would then obtain a star composed of quark matter, a sort of nuclear fluid where elementary particles circulate freely. These stars would be smaller and denser than neutron stars, and they might emit specific radiation that would allow them to be identified one day. Boson stars represent another hypothesis, this time based on the existence of particles that would obey quantum laws different from those of usual fermions, such as protons, neutrons, and electrons. Bosons, unlike fermions, can occupy the same quantum state without exclusion. This means that, under certain conditions, they could form macroscopic, unified condensates that would give rise to bodies completely different from ordinary stars. If a large amount of hypothetical boson-type particles clumped together due to gravity, it could form a boson star, stable thanks to the collective quantum properties of its matter. The existence of such an object has never been demonstrated, but it would serve as a decisive test for certain theories beyond the standard model of particle physics. Dark matter stars belong to the realm of the boldest speculations. Dark matter is a mysterious component of the universe, detected only by its gravitational effects. It is estimated to make up about 85% of all matter, but its nature remains unknown. Some theoretical models suggest that in the dense regions of the primordial universe, dark matter could have concentrated to the point of forming compact objects. In this scenario, dark matter stars would exist, drawing their energy not from nuclear fusion, but from the annihilation of dark matter particles with each other. These stars, invisible in visible light, could have illuminated the primordial universe in specific wavelengths and influenced the formation of the first galaxies. These hypotheses seem distant, almost unreal, but they are valuable. They push physics to explore the limits of its laws. What happens when the density becomes such that particles dissolve into quarks? What does the presence of matter that interacts not with light but dominates the universe imply? Can we conceive of stars that do not shine by nuclear fusion, but through yet unknown quantum mechanisms? Every time researchers ask these questions, they open a window to new discoveries. Even if these exotic stars do not exist, the calculations they inspire allow refining our models and better understanding the real objects we observe.